In this video, we shall be discussing about the Young's double slit experiment, which obviously is used to obtain the interference pattern of light waves from two coherent sources. As I mentioned earlier, that we can obtain coherent sources only from a single source, which will be easier because we need the same wavelength or the frequency in a given medium, and also the path difference must be constant, or rather the phase difference must be constant or zero. So we'll see an arrangement where we are using a double slit to obtain the coherent sources, and then we'll be uh, taking the mathematical approach to determine what the interference, that pattern that we are obtaining, and many more parameters that are associated with it, and why exactly do we need this kind of an approach. Well, the first things first, that we need a source of light which is monochromatic. Obviously we cannot use um, anything else other than monochromatic, because we need a single wavelength. So here we have a slit. Again, this is a very magnified view of what we are using, because the slits are really narrow, and the source is obviously at the middle of the point, middle from the point where we have the two slits. Now, this entire distance between those two slits is, let us say, is d. So this being d, the half distance that we are getting over here, we'll take it as d over 2 from the middle, and at a distance of capital D, we are placing a screen where we wish to obtain the interference pattern. Again, uh, this is not to scale, because the screen is at a very far distance, maintained at a very far distance. We'll know why. So we'll use this central line as of now, depicting the alignment of the middle point between the two slits on the screen, which is at the point C. And from one of those slits, this is S1, this is S2, they act as the sources of the light, the secondary wave fronts that are obtained from Huygens principle, which act as primary again to give another secondary. And we have discussed already the case of interference of light from those two slits. The question is, where will we be getting the maximum intensity and the minimum intensity? Let's look at that. Now, we'll, out of many rays that will be coming out from that slit, we'll consider just a single ray and let it fall at that point. And then we consider another ray from the source S2, which will be striking the screen at the point P. And if we are to consider the path difference between these two rays, then I'll be dropping a perpendicular from the source S1 onto the second ray at the point T, and that is a perpendicular. So this S2T is the extra path that is traveled by the second ray, because after that, from T towards P, is that will be equal to from S1 to P. However, this S2T will be very negligible, because the distance, as I say, D is much greater than this small distance which is separating the two slits. So we need to keep this one in mind, because we'll be using this condition, and well, not the mathematical case, but the physical significance of it is going to work for us. Now, in order to obtain the difference in path Why do we need to obtain the path difference first thing? Because we wish to determine what exactly is going to happen at the point P, whether we are going to get maximum intensity spot, or that is a bright spot, or a minimum intensity dark spot. Now, the amplitude in both those cases, or both those slits, with equal width of those slits taken into account, the amplitude is going to be the same for both the waves that are going to interfere. And with the amplitude being the same, as we have learnt, that the maximum intensity is going to give a bright spot, but the minimum intensity is going to be a completely dark spot. So let's determine the path difference first, which is x, which is equal to s2t. Now, in order to determine that, what we need to know is that uh, first s1p squared, as you can see. Now, from the point s1, I am considering a point M, which is exactly aligned to the point S1 on the screen, and from the point S2 as well, let me take a point N, such that Mn, the distance between them is going to be D, and between Cm and Cn, the distance is going to be D over 2, small d over 2, as we know it. And let's assume that the point P lies at a distance of y from the point C, which is aligned at the midpoint of these of the distance between the two slits. Now, with that difference, with that distance y, uh, what we wanted to know is s2t. Well, first of all, let's see what is s2p squared. Now, s2p squared is equal to, from that right angle triangle that you see, s2pn. What we know is s2p squared will be is equal to s2n squared plus np squared. And what about s1p squared? S1p squared is equal to s1m squared plus mp squared. Now, if we subtract the second equation from the first, on the left hand side we get s2p minus of s1p multiplied to s2p plus of s1p, which is a plus a minus a squared minus b squared, uh, written in that form, a plus b and a minus b multiplied. And on the right hand side, since s2n is equal to s1m, which is equal to d, of course, the two terms cancel out, and we are left with np squared minus mp squared, np squared minus mp squared. That would result in uh, y plus of d over 2 squared minus y minus d over 2 squared, as we get from the figure. And this is going to give me a plus b squared minus of a minus b squared is 4ab. So this is 4 times of y times of d over 2. And on the left hand side, what we have got is s2p minus s1p, as we know it is x. Now, as I said, that this condition is going to come up with this distance being very, very, very large, and this distance that you see over here, the distance between those two slits being very small, on that screen, as we consider s2p s1p, this angle that we are going to get is going to be very, very, very small. So these two lines, even though they have a path difference, that is going to be, well, I'll take the two slits as of now. These are the two slits. So this is the point that I've considered over here. This is the point that I'm taking the other ray. So these two distances, this small distance, well, that is very negligible when you are adding those two distances. But when you are subtracting, that difference is uh, quite uh, quite noticeable. It's just like the case of adding a very huge decimal number, 1.00001 plus 1 is going to give me a value nearly equal to 2. but subtracting the one term from the other is going to give me some value which cannot be neglected. So this is that subtraction that we have considered, and this is the addition that we have considered. And S2P, S1P can be nearly taken as D, because again the length is quite large and the angle is quite small. So S2P is nearly equal to S1P when they are getting added, is nearly equal to the distance D, which is the separation between the which is the separation between the slits and the screen. So from here, what we get is we cancel out the 2 on both the sides. And then what we get is the value of y in terms of x. So y is equal to x times of d over d. Now comes the question whether we are going to get a maximum or a minimum at that point. Now we already have discussed that we are going to end up with a maximum intensity if the path difference, which is x in this case, x is equal to an even multiple of lambda over 2, lambda being the wavelength of the monochromatic wave that is being used, and that is going to give us a maxima, and this is the condition for maxima. So if we use this value over here, we get y as the maximum position of the maximum when we have x to be equal to 2n times of lambda over 2 d over d. D over d is obviously the other term that is multiplied to x, and this is for the value x, that is 2n times of lambda over 2. Now we know that these values, for these values, n is equal to 0, 1, 2, and so on. Let's just consider the first case where n is equal to 0. Now n is equal to 0, we are going to get the first maximum at the position. We put the case of first maximum, this is the first one. So first maximum is going to be at y is equal to 0, and y, what is the distance, what is the value of y? Y is calculated from the point C up to the point P. For y being equal to 0, the point coincides, the point P coincides with C. That means that we are going to get the central maximum, or the maximum at the center, which is between the two slits, which is completely a different scenario when we are considering the case of a light traveling in a straight line path. Well, light travels in a straight line path, but because it is, we are considering the case of Huygens principle, we know that the light wave fronts are going to interfere, and they are going to interfere if you they are going to interfere, and they are going to give different spots or patches on the screen ahead of them. We would have expected a maximum only at the point M and only at the point N, because they are lying just exactly opposite to that of those two slits from which the light rays are coming. But instead of that, we are also getting a maximum. Whether we get a maximum at M or N, well, that is to be considered later. But we are getting a maximum at the point C as well. And that point C is lying exactly in the middle of the two slits. So where we would have obtained a geometrical shadow, but because it is because the light rays are interfering, we are getting an interference pattern, and out of that we are getting a maximum over there. So this is at the point C. Now the other points will all also be there, of course, but let's check whether we where we can get a minimum. So y, the distance is a generalized distance. Y can be anywhere. The point P that we have set for y from the point C, the point P actually tells us about the different points where we are going to get the maximum and the minimum as per the conditions obtained. Now, as far as the minimum is concerned, we know that the path difference being an odd multiple of lambda over 2, that will give us y minimum, and that is equal to 2n plus 1 lambda over 2 times of d over d. Now, it depends obviously on the factors capital D and small d, that where we are going to obtain the maximum and the minimum on the screen. But nevertheless, the common factor in both of them is n, which is equal to again 0, 1, 2, and so on. Now here, if we put the value of n is equal to 0, you get the minimum, the first minimum at the place that is equal to lambda d over 2d, right? So that is the point. So that is not at 0. So it will be somewhere over here where y will be equal to lambda d over 2d. And again, that distance depends on the wavelength of the light that is being used. That depends on the distance between the slits and the screen, which is capital D, and also depends on the distance between the two slits. Now, this value will be greater for greater wavelength used. For, as I said, we usually use the sodium vapor lamp, so that's pretty defined. But as far as the distances are concerned, which we will be using, the distance d is usually maintained at a distance of 1 meter, and the small distance d is usually in millimeters, so that's going to be very, very less. And that is why these points of the minima and maxima, they will be very well spaced and could be determined with clarity, with precision, by using the required telescopic arrangement. So this is the condition, these are the conditions that we are obtaining for the positions of maximum and minimum intensities. Now, between two consecutive maximums, obviously we will get, I'm taking a horizontal view of what we are going to get over there. So this is the point C that we are getting. At the point C, we are going to get a bright spot, that's for sure. And over here, again, these lines are very thick that I'm drawing over here. And on either side of that maximum, you are going to get those dark spots, which I have shaded right now. These are the minimum spots. Obviously, they are dark, completely dark, instead of the blue line that I've drawn. And then again, you are going to get two maximums followed by two minimums on either side. Obviously, the thickness or their width are to be determined right away. Right now, I'll be determining their width. So between two consecutive maximum, we are going to get a minimum, and between two consecutive minimum, we are going to get a maximum, which will help us determine those fringe widths. These are known as fringes. The dark ones are dark fringe and the bright ones are the bright fringe. Now, between those dark fringes, you will be getting a bright fringe, and we can determine that bright fringe width. Well, it's pretty simple if you consider. Now, if you remember, I had mentioned in the previous video that we are, or the video before that, that we are not using the minus sign in the odd condition, that is 2n plus of 1. We can also use 2n minus of 1. Well, for minus of 1, you will get somewhere down below, because y is taken as positive over here in the positive y-axis. We can use y in the negative y-axis, and for that we can use minus 1. But the problem lies in the case where we will be obtaining the first minimum. Now, if we take the case of minus over here, in this formula down below that I have just encircled, as you can see, in that case, if I'm considering the case of minimum 2n minus 1, so this minus over here, that would lead to, for n is equal to 0, that is the first minimum, that would lead to a negative value of position, which is not really taken into account. How can the position be negative? Yes, it can be negative when you are taking the coordinates or the axis, because I have considered a y-axis here, so I can say that I can take the position as negative, which would result in this value being a negative value, which means that the position y is going to be below the value of c. However, when we obtain the fringes in the laboratory, what we get is this horizontal type of view, and we usually do not know which one is the central fringe. So that negative and positive condition is dropped in that case, and we only consider the positive condition. So it's ideal to consider the positive conditions rather than take the negative ones. Okay, but having said that, we can use the negative condition as well. But as you see in the practical events that we use in the that we consider in the lab, these lines are very, very, very thin lines. The bright and the dark lines are very thin, and you hardly get to know which one is exactly ahead of you, in front of you, in the middle of the slits. So you cannot really consider which one is the central one. So it's just they are lined up like this, one after the other, and it's hardly, you cannot really make out which one is at the center, or which one is deviating from the center. However, because theoretically we have obtained the case of central maximum, so I can say that the first bright fringe on the upward region over here that I'm taking is at a distance of what we obtained is lambda d over 2d, and the next fringe below it in this case would be in minus lambda d over 2d. So the difference between them is going to give me the distance or the thickness of the bright fringe. And the difference between them is a lambda d over 2d minus of minus lambda d over 2d, considering their positions, which is equal to 2 times of lambda d over 2d, which leads to lambda d over d. This is the thickness or the width of a bright fringe, which exactly would be equal to the thickness of the dark fringe as well. So the fringe width that we obtain is this one, and it is completely equal in this case as for the bright and the dark spots. Now, because we have obtained the fringe width, because we know the dimensions that we have used, that is capital D and small d, it will be easier. Usually the fringe width is represented by the letter beta. So because we will be obtaining this fringe width from our experiments that we carry out in the laboratories. When you try them, you put a cross wire at that point and then slide over the cross wire to the other end. Actually, we do not take the immediate fringe, we take multiple fringes up to, let us say, 10 fringes, and the distance between 10 fringes is then taken an average of, and then you determine it. So, however, the primary thing to be concerned about is the value of fringe width is obtained, and the values of d and small d are known, from which actually we obtain the value of the wavelength. And that is exactly what we do by all those interference experiments that we carry out. We just determine the value of that wavelength of the light that we are using. So all of those arrangements only to obtain this, which is uh, pretty much valued because you have used so much of your knowledge and brain to achieve that, to obtain that wavelength, which ordinarily cannot be obtained. And also we tend to determine the refractive index of materials that are being used, uh, transparent mediums, if they are placed between any of those two paths of these light rays, which is again a separate thing to be discussed, that will be discussed at the end of the optics part, the application, another application part of it. That's not a part of the regular course, but I'll definitely be teaching that to you in extra bits that we will be discussing, but that's for later. So here we have determined the condition of maximum and minimum intensities on the screen placed in front of a Young's double slit, and we have also obtained the value of the fringe width, which is the same for the bright and the dark spots. So, and how do you maintain, how do you expect this arrangement to be perfect for you to obtain the values? Well, the arrangement will be a perfect one if you are maintaining certain things. You need to have the slit widths need to be very less or narrow, must be narrow, very, very narrow. Secondly, the distance capital D must be very large, nearly about 1 meter, as I said. Next thing, the distance between the two slits must be very, very small, usually in millimeters they are taken. And you use the same slit width so that the amplitude A1 is equal to A2 is equal to A. Because if you do not have the same amplitudes, means the slit widths are different, then what's that going to be is that that's going to result in a different amplitudes, and the minimum will not be completely dark, and hence you won't get that contrast. And if you do not get that contrast, you won't be able to study the fringe properly. So that needs to be taken into account. The amplitudes must be same, and obviously you are using the condition for coherent sources by using the Young's double slit. So coherent sources are completely there to be considered. So all these will give you a case of sustained interference pattern. These are the conditions that help you to obtain sustained interference. So that's it from this video. In the next video, we shall start with the case of diffraction of light, and then we'll end the topic with polarization as well. So that's it from this video. Thank you for watching.